Tonight we're exploring something you've definitely seen but probably never understood. Every summer day, the air around us transforms into nature's most accomplished con artist. Those shimmering water pools that appear and vanish on hot roads aren't accidents. They're demonstrations of physics so elegant they'd make any magician jealous. The atmosphere has been running the same optical scam for millions of years. We'll discover how temperature differences you can't even feel turn ordinary air into precision lenses. You'll see why the same physics that fools drivers also makes entire mountains float in the sky above cold seas. We'll follow light itself as it learns to abandon straight lines. It follows curved highways through invisible air instead. Tonight we'll uncover why these atmospheric tricks reveal something profound. They show us the hidden world existing right above our heads. So settle in. Before we begin, leave a quick note in the comments where you're listening from or one thought you're carrying tonight. I read them, and they genuinely help shape future journeys. If you'd like more nights like this, subscribe, only if you enjoy these late-night journeys. Now let's begin. Every summer afternoon, millions of drivers fall for the exact same trick. There it sits again, that pool of water shimmering on the asphalt ahead. Your brain insists it's real. Your experience says water shouldn't be sitting on a bone-dry highway. Yet there it sits, reflecting the sky like a perfect mirror. You floor the accelerator, convinced you're about to splash through standing water. But just before you reach it, the mirage dissolves into nothing. Then it reappears further ahead like a liquid ghost playing keep away. This isn't your eyes malfunctioning. This is atmospheric physics at its most mischievous. Here's what's actually orchestrating this highway con job. Pavement reaches scorching temperatures around 60 degrees Celsius. It superheats a paper-thin layer of air just millimeters above the surface. This blazing boundary zone becomes dramatically less dense than the cooler air floating above it. That invisible density difference transforms every sun-baked road into nature's most sophisticated optical workshop. The physics gets genuinely mind-blowing when you realize what you're actually seeing. Light from the bright sky encounters this density change. It bends upward at exactly the right angle to fool your visual system. You're not seeing road surface where logic demands it should be. You're viewing skylight that got redirected by heated air and sent straight to your eyes. The result, a flawless reflection of blue sky lying precisely where dark asphalt should be. Here's the truly remarkable part. The temperature difference between scorching pavement and air just 30 centimeters higher can exceed 15 degrees Celsius. That creates a refractive gradient steep enough to bend light rays through angles of 10 degrees or more. Every highway becomes a horizontal lens system stretching for kilometers. It continuously manufactures water illusions where absolutely none exist. These road mirages show extraordinary reliability, given sufficient heat and the right viewing angle. They appear with mechanical precision. This happens wherever hot surfaces meet cooler air. The exact same atmospheric con game has been fooling desert travelers for thousands of years. Our air ocean mastered this optical swindle long before humans invented highways to be deceived by. Light normally travels in perfectly straight lines through empty space at 300 million meters per second. But it faces a challenge in Earth's atmosphere it never encounters anywhere else in the universe. After racing 150 million kilometers from the sun in perfect straight lines, photons suddenly discover our air refuses to stay uniform. those light rays must navigate through invisible layers of air with different densities. This hidden landscape forces even the most determined photons to give up their straight-line trajectories entirely. The mastermind behind this optical choreography is the same principle that makes straws look bent in water glasses. Now it operates on atmospheric scales. When light travels from one air density into different air density, it changes direction at the boundary. The amount of bending depends entirely on how extreme that density difference becomes. Above hot surfaces, light doesn't hit just one sharp boundary. It navigates through hundreds of gentle density changes. Each one nudges the light ray further from its original path. Picture light following a gracefully curving highway through invisible air. A photon leaving some distant object starts traveling horizontally. But as it passes through progressively warmer and less dense air layers near hot ground, each boundary steers it slightly upward. The cumulative effect of hundreds of tiny deflections creates a smooth, curved path. This can redirect light by 15 degrees or more. That's enough to make sky appear exactly where ground should be. The physics becomes absolutely dramatic when light approaches what scientists call the critical angle. When density differences between air layers become extreme enough, light rays undergo total internal reflection. They bounce completely off the boundary between hot and cool air. This works just like light reflects off water surfaces. This atmospheric mirror effect happens most powerfully in superheated air, just above blazing pavement. Here's what genuinely astonishes physicists about this process. The atmosphere manages to guide light through these invisible curved pathways using nothing but temperature differences a few degrees apart. Even in what appears to be empty space, subtle density changes transform the sky into a three-dimensional lens system. It bends reality in ways our brains never evolved to expect. The air itself becomes a master optical engineer, sculpting light into impossible shapes. Earth's atmosphere occasionally decides to completely violate its own rules about temperature. Normally, air gets cooler as you climb higher into the sky. Mountain climbers know this. Pilots depend on it. But sometimes the atmosphere flips this arrangement entirely upside down. These rebellious zones create what scientists call temperature inversion layers. These atmospheric rebellion zones manufacture some of nature's most spectacular optical illusions. Temperature inversions happen when a layer of warm air sits on top of cooler air below. This backwards arrangement creates perfect conditions for atmospheric mischief on a grand scale. The density difference between these inverted layers becomes so extreme that light gets bent through impossible angles. This creates mirages that make entire landscapes appear to float in midair. These inverted zones form most dramatically over cold ocean surfaces during summer months. When warm air masses drift over frigid seawater, they create stable layers of backwards temperature gradients. These can stretch for hundreds of kilometers. Ships sailing through these regions suddenly find themselves in atmospheric funhouses. Distant objects appear to hover above the horizon, completely detached from reality. Temperature inversions don't limit themselves to ocean environments. They form over frozen lakes in winter when warm air slides across ice surfaces. They develop in desert regions during early morning hours. Overnight cooling creates cold surface layers beneath warmer air above. They even occur in urban environments where concrete and asphalt cool rapidly after sunset. The optical effects produced by these inverted temperature layers can be absolutely spectacular. Distant mountains appear to float completely above the horizon. Cities seem to hover in midair like cosmic space stations. Ships sailing beyond the normal horizon become visible as ghostly images hanging in the sky. Islands that should be hidden by Earth's curvature suddenly appear suspended above the water like floating continents. What makes temperature inversion mirages particularly mind-bending is their stability. Unlike the dancing highway mirages that shimmer and fluctuate constantly, inversion layer illusions can remain perfectly steady for hours at a time. Entire phantom landscapes hang motionless in the sky. These create optical experiences so convincing they've been mistaken for real floating cities throughout human history. What if the atmosphere doesn't limit itself to just one type of optical trickery? Like a master magician with an entire repertoire of illusions, our air ocean has developed several distinctly different mirage varieties. Each one is designed to fool human perception in specific ways. Understanding these different atmospheric magic tricks reveals just how sophisticated Earth's invisible optical workshop actually operates. Inferior mirages represent the atmosphere's most common performance. These happen when hot surfaces create the dancing water pools we see on summer highways. The image appears below the actual object, hence inferior meaning lower in position. Hot desert sand creates inferior mirages that place phantom lakes beneath the horizon. These illusions fool people into seeing water precisely where their survival instincts desperately hope to find it. Superior mirages perform the opposite magic trick entirely. These form when temperature inversion layers make objects appear above their actual positions. Cold ocean surfaces create perfect conditions for superior mirages that suspend entire landscapes in the sky. Ships beyond the normal horizon suddenly become visible as ghostly images floating above the water. Mountains appear to hover in midair like impossible aerial castles. Lateral mirages demonstrate the atmosphere's ability to displace objects sideways rather than up or down. These exotic illusions happen when vertical temperature gradients create horizontal optical displacement. Objects appear shifted to the left or right of their actual positions. This creates the unsettling experience of watching reality slide sideways before your eyes. Fata Morgana represents the atmosphere's most elaborate and theatrical performance. Named after the legendary sorceress Morgan Le Fay, these complex mirages create entire phantom landscapes. They can include multiple inverted and upright images stacked on top of each other. Fata Morgana illusions can make distant ships appear as towering castles. They transform flat horizons into elaborate architectural fantasies. Green flash mirages occur during sunrise and sunset when atmospheric refraction separates the sun's light into component colors. Just as the sun disappears below the horizon, observers occasionally witness a brief green flash. This happens as the last sliver of green light gets bent around Earth's curvature by atmospheric lenses. Each mirage type reveals specific atmospheric conditions and demonstrates particular optical principles. The atmosphere's complete magic show repertoire proves something remarkable. Our invisible air ocean operates as an incredibly sophisticated optical laboratory. Scientists have discovered something that might change how you think about atmospheric illusions forever. Mirages aren't examples of nature breaking its own rules or optical systems malfunctioning. They're demonstrations of physics working with absolute precision under specific atmospheric conditions. Every dancing highway mirage and floating mountain represents light following the exact laws it's supposed to follow. This happens when density gradients bend light's path through three-dimensional space. Scientists use mirages as natural laboratories for studying atmospheric physics in real time. These optical phenomena provide direct visual evidence of invisible temperature gradients. They reveal air density variations and atmospheric boundary layers. These would otherwise require sophisticated instruments to detect. When you spot a mirage, you're witnessing atmospheric science in action. The mathematics governing mirage formation follows predictable equations that physicists have understood for over a century. Snell's law describes exactly how light bends when traveling between materials of different optical densities. The refractive index gradients that create atmospheric lenses can be calculated precisely. This calculation uses temperature and pressure measurements. Nothing random or magical happens during mirage formation, just elegant physics operating according to fundamental optical principles. Modern meteorologists actually rely on mirage observations to gather information about atmospheric conditions. The type, intensity, and behavior of mirages provide valuable data. This includes temperature profiles, wind patterns, and air mass stability. All of this helps improve weather prediction models. Atmospheric physicists study mirage formation to better understand heat transfer, convection patterns, and boundary layer dynamics in Earth's lower atmosphere. The same optical principles that create Earth's atmospheric mirages operate throughout the universe. This happens wherever temperature gradients exist in gaseous environments. Astronomers observe similar light-bending phenomena in stellar atmospheres. They see them in planetary atmospheres on other worlds and in the interstellar medium between star systems. The atmospheric magic tricks we witness on summer highways represent universal physics principles. These shape light behavior across the entire cosmos. Rather than seeing mirages as atmospheric lies or optical deceptions, we might better understand them differently. They're glimpses into the normally invisible architecture of our air ocean. They reveal the hidden temperature landscapes that surround us constantly. They show the three-dimensional density structures that light navigates every second. Every mirage represents a moment when the atmosphere's invisible complexity becomes temporarily visible. This offers us brief windows into the sophisticated optical engineering that operates continuously above our heads. Light has been following the same traffic rules for billions of years. This happened long before humans discovered them and gave them fancy names. When a photon traveling through one material hits the boundary with a different material, it doesn't just barrel straight through like some cosmic bulldozer. It politely changes direction according to a mathematical relationship. This relationship governs every optical interaction in the universe. Scientists call it Snell's law. You've witnessed this principle countless times without realizing it. Drop a straw into a glass of water and watch it appear to bend at the surface. That's Snell's law in action. Light traveling from the straw through water hits the water-air boundary. It bends toward your eyes at a different angle than it traveled underwater. The straw didn't actually bend, light just took a detour at the boundary. This fooled your visual system into seeing something impossible. This same geometric relationship now operates on atmospheric scales across every sun-baked highway and desert landscape on Earth. Instead of light traveling from water into air, it journeys from dense cool air into less dense hot air. The principle remains identical, but the playing field has expanded. Now it stretches from water glasses to entire atmospheric layers extending for kilometers. Here's where atmospheric refraction gets genuinely fascinating. The amount of bending depends entirely on how different those two materials are from each other. Water and air have dramatically different optical densities. That's why straws appear severely bent. Cool air and hot air have much subtler differences, so light bends through smaller angles. But when hot surfaces create extreme temperature gradients, even those small differences add up to dramatic optical effects. The mathematical elegance of Snell's law means atmospheric mirages aren't random accidents. They're predictable consequences of known physics principles. Given specific temperature and pressure conditions, physicists can calculate exactly how much light will bend. They can predict where mirages will appear and how intense those optical illusions will become. The atmosphere follows the same rules that govern every lens in every telescope, camera, and eyeball on the planet. What makes atmospheric applications of Snell's law particularly remarkable is their scale. Instead of light bending once at a single surface, photons navigate through hundreds of subtle boundaries. They travel through layers of air with gradually changing densities. Each tiny course correction follows Snell's law precisely. The cumulative effect creates the curved light paths that manufacture impossible optical experiences above every hot surface on Earth. Dense cold air packs its molecules together tightly, creating regions of high optical density. These regions slow light down and bend its path significantly. Hot air spreads its molecules farther apart, creating zones of low optical density. These zones speed light up and bend its path in the opposite direction. Light traveling from dense regions to sparse regions experiences something interesting. It's like the optical equivalent of a car accelerating from city traffic into open highway. Temperature differences that seem trivial to humans create substantial optical challenges for photons. A 15-degree difference between hot asphalt and cool air above it produces enough density contrast to redirect light. This can bend light through angles of 10 degrees or more. That's sufficient bending to make sky appear where ground should be, or ground appear where sky should be, depending on the viewing geometry. But here's where atmospheric physics becomes genuinely mind-bending. Light doesn't encounter just one dramatic density change like the sharp boundary between water and air. Instead, photons navigate through gradual transitions where air density changes smoothly. This happens over distances of centimeters or meters. This creates curved optical paths rather than sharp angular bends. It's like following a gently winding mountain road instead of making abrupt 90-degree turns. The density gradient becomes steepest in the thin layer immediately above hot surfaces. Temperatures can change by 20 degrees across a vertical distance of just a few centimeters. This creates what physicists call a strong refractive index gradient. It's essentially an invisible lens made of nothing but heated air. This lens can focus, defocus, and redirect light with the precision of expensive optical equipment. Light traveling through these density gradients experiences continuously changing optical conditions. It's like driving through a landscape where the speed limit changes every few meters. Each infinitesimal layer of air with a slightly different density nudges the light ray a tiny bit further from its original trajectory. The cumulative effect of thousands of microscopic course corrections creates the smooth, curved paths. These guide skylight down to road surfaces and create those impossible pools of reflected blue sky on bone-dry asphalt. Most people imagine light bending like a ball bouncing off a wall. They picture it hitting some barrier and ricocheting in a new direction. But atmospheric refraction operates more like a river, gradually changing course as it flows downhill. Each section of the journey smoothly curves into the next. Light doesn't get whacked into a new direction. It gets gently persuaded to follow an increasingly curved path through the invisible landscape of air density variations. This progressive bending happens because real atmospheric temperature gradients don't create sharp boundaries between different air types. Instead, they produce smooth transitions where hot air near the ground gradually becomes cooler air higher up. Light traveling through these graduated zones experiences what physicists call continuous refraction. This creates a steady curving process that can redirect photons through dramatic angles. It does this without any sudden direction changes. Picture a photon's journey like following a spiral highway ramp. The light ray starts traveling horizontally toward your eyes. But as it passes through progressively less dense air layers near a hot surface, each layer bends it slightly more upward. The individual deflections are tiny, maybe fractions of a degree each. But hundreds of these microscopic course corrections add up to total direction changes of 15 degrees or more. The beauty of progressive refraction lies in its smoothness. Sharp optical boundaries create harsh, unstable images that flicker and dance wildly. But gradual density transitions produce stable, steady mirages that can remain perfectly motionless for minutes at a time. This is why superior mirages over cold ocean surfaces can create rock-steady illusions of floating islands and suspended ships. These look convincingly solid and permanent. Scientists have discovered that the steepness of temperature gradients determines how dramatically light curves through atmospheric layers. Gentle gradients create subtle optical effects that might make distant objects appear slightly displaced or distorted. Extreme gradients can curve light through such severe angles that entire landscapes appear completely inverted. This creates the upside-down images characteristic of complex mirage phenomena. The mathematical description of progressive refraction requires calculus to handle the continuously changing optical conditions. These are the conditions that photons encounter during their atmospheric journey. Unlike simple Snell's law calculations that work for discrete boundaries, progressive refraction involves integrating the cumulative effects. It must account for countless infinitesimal deflections along curved optical paths. Sometimes atmospheric conditions become so extreme that light gives up trying to continue its journey entirely. Instead, it bounces back like a ball hitting a trampoline. This optical surrender happens when photons encounter what physicists call the critical angle. This represents a precise geometric threshold where refraction stops working and reflection takes over completely. When this occurs in Earth's atmosphere, the air itself becomes a perfect mirror lying horizontally above hot surfaces. Total internal reflection was first discovered in water and glass. There it creates the silvery mirror effect you see when looking up at the underside of a swimming pool surface from underwater. Light traveling through a denser medium toward a less dense medium can only refract successfully under certain conditions. It must approach the boundary at shallow enough angles. If the approach angle becomes too steep, the mathematics of Snell's law breaks down completely. Reflection becomes the only optical option available. The same physics now operates in the superheated air, just millimeters above scorching asphalt and desert sand. When temperature differences between hot surface air and cooler air above become sufficiently extreme, they create optical density contrasts. These approach those found between water and air. Light from the sky traveling downward toward these hot surfaces hits the critical angle threshold. It gets reflected back upward with mirror-like precision. This atmospheric mirror effect explains why highway mirages can create such convincing water illusions. Total internal reflection produces the same optical experience as looking at an actual water surface. Skylight gets reflected upward with the geometric perfection of a polished mirror. Your brain interprets this reflected sky image as water because that's the most common experience associated with seeing sky reflections. The critical angle threshold varies depending on exactly how extreme the temperature gradients become. Moderately hot surfaces might create weak total internal reflection that produces faint, unstable mirages. Brutally hot surfaces can generate such strong optical density contrasts that they reflect skylight with the efficiency of actual mirrors. This creates mirages so convincing they've fooled travelers into making detours toward non-existent water sources. What makes atmospheric total internal reflection genuinely extraordinary is its invisibility. The mirror surface exists only as a mathematical construct. It's a geometric plane where optical physics changes behavior completely. You can't see the mirror itself, only its effects. Light traveling in one direction gets reflected back perfectly, while light traveling in slightly different directions passes through normally. The atmosphere creates invisible mirrors that exist only for photons approaching from specific angles. These are like optical trapdoors that open and close based on geometric rules rather than physical structures. The atmosphere operates like an ambitious theater director, constantly adjusting lighting effects. It works to create more dramatic optical performances. Subtle temperature differences produce gentle, barely noticeable light bending. But extreme temperature contrasts transform the air into powerful optical instruments. These instruments can manufacture spectacular illusions that completely disconnect visual experience from physical reality. Refractive index represents the mathematical measure of how much different materials bend light compared to empty space. Air has a refractive index very close to 1.0. This means it barely affects light's behavior under normal temperature conditions. But as air temperature increases, its refractive index decreases in a predictable mathematical relationship. Hot air becomes optically thinner than cool air. This creates the density contrasts that redirect photons through increasingly dramatic angles. A temperature difference of just 5 degrees between air layers produces subtle optical effects. These might make distant objects appear slightly shimmery or displaced. But when temperature contrasts reach 20 degrees or more across short vertical distances, the refractive index differences become substantial. They become substantial enough to curve light through angles approaching 45 degrees. That's sufficient bending to make the horizon appear to flip completely upside down. Desert environments and sun-baked urban surfaces excel at creating these extreme optical conditions. Black asphalt can reach temperatures of 70 degrees Celsius, while air just 1 meter above remains at 35 degrees Celsius. This creates a temperature gradient steep enough to create refractive index variations comparable to those between different types of optical glass. The atmosphere essentially manufactures precision lenses using nothing but heated air and physics. The mathematical relationship between temperature differences and mirage intensity follows predictable curves. These allow meteorologists to forecast optical conditions just like they predict weather patterns. Given specific temperature and pressure measurements, scientists can calculate exactly how strong atmospheric lenses will become. They can predict how far mirages will be visible and what types of optical illusions will dominate different geographic regions. But here's where atmospheric optics reveals its most impressive capability. Multiple temperature inversion layers can stack on top of each other. This creates complex optical systems with several different focal lengths operating simultaneously. This layered lens architecture can produce the extraordinary Fata Morgana phenomena. These create scenes where multiple inverted and upright images appear stacked vertically. The result is impossible landscapes that look like scenes from alternate dimensions. The atmosphere's pursuit of maximum optical drama sometimes generates visual experiences so bizarre they challenge our fundamental understanding of what reality should look like. Earth's atmosphere usually follows a simple, predictable rule that every mountain climber knows by heart. The higher you climb, the colder it gets. This temperature gradient has governed atmospheric behavior for billions of years. It creates the orderly vertical arrangement that makes weather forecasting possible. But sometimes the atmosphere decides to rebel against its own fundamental organizing principle. It flips this temperature structure completely upside down. Temperature inversion layers represent the atmosphere's most mischievous mood swings. These are periods when warm air sits on top of cool air, like oil floating on water. This backwards arrangement violates every expectation about how air should behave. It creates atmospheric conditions so unusual they transform the sky into a natural optical laboratory. This laboratory can manufacture impossible visual experiences. These inverted temperature zones don't happen randomly or accidentally. They require specific meteorological conditions that essentially force the atmosphere to reorganize itself. It reorganizes in opposition to its normal temperature profile. When these conditions align, they create stable layers of backwards temperature gradients. These can persist for hours or even days at a time. The optical consequences of temperature inversions become immediately apparent to anyone unlucky enough to witness them. Light traveling through these backwards temperature layers gets bent through extreme angles. Entire landscapes can appear to float in midair. Ships sailing beyond the normal horizon suddenly become visible as ghostly images hanging in the sky. Mountains appear to hover above their actual positions like impossible aerial islands. What makes temperature inversions genuinely fascinating is their stability. It contrasts with the dancing, shimmering mirages created by ground heating. Inferior mirages flicker and fluctuate constantly near hot surfaces. Turbulent air currents drive that. Inversion layer mirages can remain perfectly steady. They hold their focus steady for extended periods. Scientists have discovered that temperature inversions don't just create random optical chaos. They follow predictable patterns based on the strength and thickness of the inverted layers. Weak inversions might produce subtle image displacement effects. Strong inversions can create multiple stacked images of the same object. Each one appears inverted or upright. It depends on the specific optical path light follows through the backwards temperature architecture. The most dramatic temperature inversions start with the ground itself becoming a massive heating element. It pumps thermal energy into the lowest layers of atmosphere with the intensity of a planetary furnace. Desert sand, concrete parking lots, or black asphalt reach temperatures exceeding about 60 degrees Celsius. They don't just warm the air gently. They create vertical temperature gradients so extreme they challenge fundamental assumptions. These challenge the assumption that air gets cooler with altitude. during peak heating conditions. The temperature difference between scorching ground surfaces and air just 2 meters above can exceed 25 degrees Celsius. This creates what meteorologists call a superadiabatic lapse rate. This represents a temperature gradient so steep it violates normal atmospheric stability rules. The result is a vertical sauna environment where air temperature changes more rapidly with altitude than physics normally allows. These extreme ground heating effects produce layered atmospheric structures that resemble invisible geological formations. But these are made of temperature variations instead of rock. The hottest air hugs the surface in a thin boundary layer just centimeters thick. Above that sits slightly cooler air in a transition zone. Higher still, normal atmospheric temperature gradients eventually resume their predictable behavior. But here's where ground heating creates its most spectacular optical effects. Light traveling through these stacked temperature layers encounters optical density changes. These are equivalent to looking through multiple sheets of different types of glass. Each layer bends light by slightly different amounts. This creates complex curved paths that can redirect photons through angles approaching 90 degrees. The vertical temperature structure created by intense ground heating operates like a natural optical laboratory. It has multiple focal lengths working simultaneously. Light from objects at different distances gets bent by different amounts as it travels through this layered atmosphere. This creates the possibility for multiple images of the same object to appear at different apparent positions in the sky. Ground heating inversions also explain why highway mirages become most intense during the hottest part of summer afternoons. The combination of maximum solar heating and minimal wind creates perfect conditions for establishing steep temperature gradients. These can persist for hours. The asphalt essentially becomes a horizontal heating element stretching for kilometers. It continuously pumps thermal energy into the atmosphere and maintains the extreme temperature differences required for dramatic optical effects. Cold ocean water possesses a remarkable talent for creating atmospheric conditions that would make any science fiction writer jealous. When warm air masses drift over frigid sea surfaces, they encounter natural refrigeration on a massive scale. It flips normal atmospheric temperature relationships completely upside down. The result: perfect conditions for superior mirages that can make entire cities appear to float in the sky like cosmic space stations. Marine temperature inversions operate through elegantly simple physics. Ocean water maintains relatively stable temperatures year-round due to its enormous thermal mass. This is the same property that makes beach towns cooler in summer and warmer in winter than inland areas. When warm continental air masses flow over these cold ocean surfaces, the water acts like a gigantic heat sink. It rapidly cools the lowest atmospheric layers while leaving warmer air floating above. This creates the opposite temperature structure from ground heating inversions. Instead of hot air at the bottom and cool air above, marine inversions establish cool air near the water surface. Warm air gets layered on top. Light traveling through these inverted temperature zones gets bent upward rather than downward. This makes distant objects appear elevated above their actual positions rather than reflected below them. The optical effects produced by marine temperature inversions can be absolutely spectacular. Ships sailing beyond the normal horizon become visible as elevated images floating in the sky. Distant coastlines appear to hover above the water like suspended landscapes. Islands that should be hidden by Earth's curvature suddenly become visible. They appear as ghostly aerial phantoms hanging motionless above the horizon. Arctic and subarctic regions experience the most dramatic marine inversion effects due to the extreme temperature contrasts. These occur between ice-cold water and relatively warm air masses. During certain weather conditions, these regions can produce Fata Morgana phenomena so complex they create entire phantom landscapes. These are complete with inverted castles, floating mountains, and impossible architectural fantasies. What makes marine inversions particularly reliable is their stability over time and distance. Marine inversions can extend for hundreds of kilometers across ocean surfaces. Unlike the turbulent air currents that make ground-heating mirages shimmer and dance, they can remain optically stable for many hours. This stability allows complex superior mirages to develop fully. It also maintains their impossible imagery long enough for detailed observation and photography. Every clear night, the ground surface participates in a cosmic cooling process that would impress any refrigeration engineer. After sunset, Earth's surface begins radiating accumulated heat directly into the cold vacuum of space. It cools so efficiently that it can become several degrees colder than the air floating just meters above it. This overnight refrigeration process creates temperature inversions that set the stage for some of nature's most spectacular dawn mirage displays. Radiative cooling operates like a planetary heat pump that works in reverse. During daylight hours, the ground absorbs massive amounts of solar energy and becomes much hotter than the surrounding air. But after dark, this energy flow reverses completely. The ground surface radiates infrared energy upward toward space. It does this at wavelengths that pass through the atmosphere almost without interference. This cools the surface rapidly while leaving warmer air trapped above. By dawn, this overnight cooling process can create temperature inversions. Ground-level air becomes 10 degrees or more colder than air just 10 meters above the surface. These inverted temperature gradients produce perfect conditions for superior mirages. These make distant objects appear elevated, stretched, or completely detached from their normal positions on the landscape. The most spectacular radiative cooling effects occur in desert regions where clear skies and dry air allow maximum heat radiation towards space. Desert surfaces can cool so rapidly overnight that they create multiple stacked temperature inversion layers. Each one contributes to complex optical effects that can produce extraordinary Fata Morgana displays at sunrise. Early morning travelers in desert regions occasionally witness impossible landscapes. Distant mountains appear to float completely above the horizon, their images stretched vertically into towering spires. Or they get compressed horizontally into impossible architectural fantasies. These dawn mirages represent some of the most complex optical phenomena in Earth's atmosphere. They're created by the overnight temperature inversion architecture that radiative cooling establishes with clockwork reliability. The timing of these radiative cooling mirages follows predictable patterns based on local geography and weather conditions. Clear skies and low humidity maximize cooling rates and create the strongest temperature inversions. Wind disrupts the layered temperature structure and destroys the optical conditions necessary for complex mirage formation. The brief window between maximum overnight cooling and sunrise heating is often the best. It provides the most spectacular superior mirage displays of the entire day. High pressure and low pressure systems don't just determine whether you need an umbrella. They also function as massive atmospheric lens manufacturing operations. They can optimize or completely destroy conditions for mirage formation. Understanding how weather patterns influence optical phenomena reveals something remarkable. The atmosphere operates like a continent-sized optical laboratory. Meteorological conditions determine what types of visual illusions become possible. High-pressure systems excel at creating ideal mirage conditions through their talent for atmospheric organization. These weather patterns generate sinking air, masses that compress and warm as they descend. This creates stable temperature layering that can persist for days at a time. The subsiding air suppresses turbulence and cloud formation, producing clear skies and minimal wind. These represent perfect conditions for establishing the undisturbed temperature gradients that sophisticated mirages require. Low-pressure systems typically destroy mirage conditions through atmospheric chaos. Rising air currents, cloud formation, and turbulent winds disrupt the delicate temperature layering that optical illusions need to develop properly. The mixing and churning associated with low-pressure weather patterns scramble temperature gradients faster than they can establish stable optical properties. But weather systems can also create exotic mirage conditions that don't occur under normal atmospheric circumstances. Frontal boundaries, the transition zones between different air masses, occasionally produce complex temperature structures. These have multiple inversion layers stacked on top of each other. These meteorological sandwich arrangements can generate extraordinary Fata Morgana phenomena. Single objects appear as multiple stacked images. Each one is inverted or upright. It depends on which optical path light follows through the layered atmosphere. Seasonal weather patterns also influence the types and intensity of mirages. Different geographic regions experience these throughout the year. Desert areas experience peak mirage activity during hot, dry high-pressure periods. Coastal regions see maximum superior mirage activity when continental high-pressure systems push warm air over cold ocean surfaces. Arctic regions can produce spectacular ice mirage displays when specific combinations of high pressure, clear skies, and extreme temperature contrasts align. Meteorologists have discovered that they can actually forecast optimal mirage viewing conditions by monitoring atmospheric pressure patterns. They track temperature gradients and wind speeds. Some weather services in regions known for spectacular mirage phenomena now include optical conditions in their specialized forecasts. These serve photographers and atmospheric optics enthusiasts. The atmosphere's optical behavior has become as predictable as traditional weather patterns. This reveals that even the most magical-seeming natural phenomena follow comprehensible physical rules. These rules are governed by meteorological processes. Every con artist needs a signature move. The atmosphere's most reliable crowd pleaser involves convincing millions of people they're seeing water where none exists. Inferior mirages represent the atmosphere's bread and butter optical illusion. This is the classic highway shimmer that's fooled more humans than any other natural phenomenon in Earth's history. These ground-level reflections happen so frequently that most people don't even realize they're witnessing advanced atmospheric physics in action. The term inferior doesn't mean these mirages are low-quality performances. It simply indicates that the false image appears below the actual object. It is inferior in terms of position rather than optical sophistication. When you see sky reflected on hot asphalt, you're viewing an inferior mirage. The image of blue sky appears beneath its actual location in the heavens. Inferior mirages require remarkably simple atmospheric conditions to manufacture their illusions. Any surface that becomes significantly hotter than the air above it can create the density gradients necessary for this type of optical trickery. Hot sand, sun-baked concrete, black asphalt, even heated metal surfaces can all function as inferior mirage generators. This works during appropriate weather conditions. The optical mechanics behind inferior mirages follow predictable physical laws. Light from the sky travels downward toward the hot surface. It encounters the extreme density gradient in the superheated boundary layer and gets bent back upward through total internal reflection. This creates a perfect mirror effect using nothing but heated air and the fundamental properties of light refraction. What makes inferior mirages genuinely fascinating is their reliability across different environments and climates. Desert travelers encounter them as classic oasis illusions. Highway drivers see them as water pools on hot roads. Beach visitors witness them on scorching sand surfaces. The same atmospheric physics operates whether you're crossing the Sahara or driving through a shopping mall parking lot on a summer afternoon. Inferior mirages also demonstrate remarkable stability despite the turbulent air currents that create them. While the images shimmer and dance due to constantly changing thermal conditions, the basic mirage structure can persist for hours. This happens as long as surface heating continues. The atmosphere maintains these optical illusions with the consistency of a well-rehearsed magic trick. It's performed by a master showman who never breaks character or reveals the secret behind the impossible visual experience. Superior mirages operate like the atmosphere's most sophisticated home theater system. They project images of distant objects onto an invisible screen floating above the horizon. Unlike their inferior cousins that reflect images downward, superior mirages elevate objects above their actual positions. This creates the mind-bending spectacle of ships sailing through the sky and mountains floating like impossible aerial islands. The atmospheric conditions required for superior mirages represent the exact opposite of those that create highway water pools. Instead of hot surfaces heating air from below, superior mirages need cold surfaces that cool air from the bottom. Warmer air floats above. This inverted temperature structure acts like an upside-down lens that bends light upward rather than reflecting it downward. Cold ocean surfaces excel at creating ideal superior mirage conditions during specific weather patterns. When warm air masses flow over frigid seawater, they establish stable temperature inversions that can extend for hundreds of kilometers. These marine conditions produce some of the most spectacular superior mirages on Earth. Cool. They make distant ships appear as floating ghost vessels and transform ordinary horizons into impossible elevated landscapes. Arctic regions generate particularly dramatic superior mirage displays due to the extreme temperature contrasts. These occur between ice-cold surfaces and relatively warm air masses above. During optimal conditions, entire mountain ranges can appear to hover completely above the horizon. Their images get stretched vertically into towering spires or compressed horizontally into fantastic architectural impossibilities. The stability of superior mirages distinguishes them from the constantly shifting inferior mirages created by surface heating. Marine temperature inversions can remain optically stable for many hours. This allows complex elevated images to develop and persist long enough for detailed observation. These steady atmospheric conditions enable superior mirages to create convincing illusions of floating cities, suspended islands, and aerial landscapes. Superior mirages also possess the remarkable ability to make objects visible that should be hidden beyond Earth's curvature. by bending light through extreme upward angles. These atmospheric lenses can effectively extend the visual horizon. They reveal ships, coastlines, and land masses that lie beyond the normal limits of direct observation. The atmosphere essentially provides a natural periscope service that allows observers to see around the planet's curved surface. Earth's curvature usually serves as a reliable cosmic privacy screen. It hides distant objects behind the planetary bulge with mathematical precision. Ships sailing beyond approximately 20 kilometers disappear hull first, then mast last. This follows predictable geometric rules that have governed ocean navigation for centuries. But sometimes the atmosphere decides to completely ignore these geometric limitations. It creates its own long-distance viewing service. Superrefraction represents the atmosphere's most impressive feat of optical engineering. It can bend light through such extreme angles that it follows Earth's curvature like a cosmic fiber optic cable. This phenomenon allows observers to see objects that should be mathematically impossible to view directly. It effectively extends the visual horizon well beyond its normal geometric boundaries. The physics behind superrefraction requires atmospheric conditions so precisely calibrated they occur only during specific combinations of temperature, pressure, and humidity. Strong temperature inversions must extend continuously over vast distances. These create optical ducts that can guide light along curved paths that mirror Earth's surface curvature. These atmospheric waveguides function like natural optical fibers made of temperature-stratified air. Arctic and subarctic regions experience the most dramatic superrefraction phenomena due to their stable, layered atmospheric conditions during certain weather patterns. Observers in these regions occasionally witness impossible scenes. Land masses hundreds of kilometers away become visible as clear, detailed images above the horizon. Entire mountain ranges that should be hidden by Earth's curvature suddenly appear as elevated phantoms floating in the sky. Coastal areas also produce remarkable superrefraction effects when specific marine weather conditions align properly. Ships sailing well beyond the normal horizon can become visible as elevated images that appear to hover above the water surface. These marine superrefraction events can extend visual range by factors of 2 or 3. This essentially provides natural telescope capabilities using nothing but atmospheric physics. The military and maritime communities have long recognized superrefraction as both a valuable observation tool and a significant navigation hazard. Radar systems can experience similar atmospheric ducting effects that extend their normal range dramatically. But they also create false target appearances. Understanding superrefraction behavior has become essential for accurate weather forecasting, maritime navigation, and atmospheric physics research. The atmosphere occasionally abandons its role as a subtle optical engineer. Instead, it embraces its inner funhouse mirror designer, stretching and compressing objects into bizarre shapes that would make any carnival attraction jealous. Vertical distortion represents the atmosphere's most playful approach to bending reality. It creates optical experiences where familiar objects transform into impossible geometric fantasies. These atmospheric stretching effects happen when light travels through multiple temperature inversion layers stacked on top of each other like optical pancakes. Each layer bends light by slightly different amounts. This creates complex refraction patterns that can elongate objects vertically, compress them horizontally, or twist them into shapes that violate every expectation. They violate expectations about how things should appear in the real world. Ships sailing near the horizon become particularly susceptible to atmospheric distortion effects. What should appear as a normal vessel can transform into a towering vertical structure. This looks more like a floating skyscraper than a maritime craft. The ship's hull might appear stretched into impossible proportions, while its superstructure gets compressed into a thin horizontal line. This creates optical experiences that challenge observers' fundamental understanding of object permanence. Distant mountains and coastlines also fall victim to atmospheric distortion magic. Temperature inversion layers can stretch mountain peaks into needle-like spires that tower impossibly high above their actual elevations. Conversely, the same atmospheric conditions might compress entire mountain ranges into thin horizontal bands. These appear to float just above the horizon like geographical ribbons suspended in midair. The mathematical complexity of predicting vertical distortion effects requires sophisticated atmospheric modeling. This must account for multiple interacting temperature gradients operating simultaneously, unlike simple superior or inferior mirages that follow relatively straightforward optical rules. Vertical distortion involves complex interactions between several different refractive layers. These can produce almost limitless varieties of impossible shapes. Antarctic research stations regularly document some of Earth's most extreme vertical distortion phenomena. The combination of extremely stable atmospheric conditions and dramatic temperature contrasts creates ideal circumstances for complex, multi-layer refractive effects. Scientists working in these regions have photographed ice formations that appear stretched into cathedral-like spires. They've seen compressed research buildings that look like horizontal lines floating in space. They've witnessed distant mountain ranges that seem to undulate like geological waves frozen in time. When the atmosphere really wants to show off, it abandons simple single-effect illusions. Instead, it performs elaborate optical magic combinations that would challenge even the most experienced stage magician. These complex mirage phenomena represent the pinnacle of atmospheric optical engineering. They combine multiple physical principles into spectacular displays that can create entire phantom landscapes complete with impossible architecture and surreal color effects. The green flash represents one of nature's briefest but most sought-after optical performances. Just as the sun disappears below the horizon in clear weather, atmospheric refraction can separate the solar disk into component colors. It works like a natural prism. The final sliver of green light gets bent more strongly than red light due to its shorter wavelength. It occasionally appears as a brilliant emerald flash that lasts only seconds but creates an unforgettable optical experience. Green flash sightings require almost perfect atmospheric conditions. These include clear horizons, stable air masses, and minimal atmospheric turbulence. Ocean environments provide ideal circumstances because water surfaces create the unobstructed horizons and stable atmospheric conditions necessary for this delicate optical phenomenon. Even slight atmospheric disturbances can destroy the precise refraction geometry required for green flash formation. Fata Morgana phenomena represent the atmosphere's most ambitious and complex mirage productions. Named after the legendary sorceress Morgan Le Fay, these elaborate optical illusions can create entire phantom landscapes. These include multiple inverted and upright images stacked vertically like impossible architectural fantasies. Fata Morgana effects require multiple temperature inversion layers operating simultaneously. Each contributes different optical elements to the final composite illusion. The most spectacular Fata Morgana displays occur in polar regions where stable, layered atmospheric conditions can persist for extended periods. These environments occasionally produce phantom landscapes so detailed and convincing they include recognizable architectural features. These features look like towers, castles, and elaborate geometric structures that appear to exist in parallel dimensions just above the normal horizon. Arctic explorers throughout history have documented Fata Morgana phenomena so complex they've inspired legends of floating cities, aerial kingdoms, and impossible realms. These exist just beyond the edge of normal reality. These optical experiences became so culturally significant that many maritime cultures developed specific mythologies to explain the impossible landscapes. These occasionally materialized above cold ocean surfaces. Modern atmospheric physicists have discovered that Fata Morgana complexity depends on the precise arrangement of multiple refractive layers. These have specific temperature and humidity gradients. Computer modeling now allows scientists to predict optimal viewing conditions for complex mirage formation. This reveals that even the most magical-seeming natural phenomena follow comprehensible physical laws governing atmospheric optics. The atmosphere's most elaborate magic tricks represent sophisticated applications of fundamental physics principles rather than violations of natural law. Highway departments across the world have accidentally become partners in one of nature's most consistent optical manufacturing operations. Every mile of black asphalt laid down creates a potential mirage factory that activates automatically whenever summer temperatures climb high enough. These road surfaces don't just absorb solar energy. They transform it into precisely calibrated optical illusions that fool millions of drivers with industrial-scale efficiency. Black asphalt possesses almost supernatural talents for collecting and concentrating solar heat. While most surfaces reflect a significant portion of incoming sunlight, asphalt absorbs over 95% of solar radiation. It converts it directly into thermal energy. During peak summer conditions, highway surfaces can reach temperatures exceeding 70 degrees Celsius. That's hot enough to cook an egg or inflict serious burns on bare skin within seconds. This extreme surface heating creates what physicists call a boundary layer thermal gradient. This represents a paper-thin zone just millimeters above the pavement where temperature changes by 20 degrees or more. This happens across a vertical distance smaller than a pencil's width. This invisible temperature cliff generates refractive index differences strong enough to bend light sharply. It transforms ordinary highway surfaces into horizontal lens systems stretching for kilometers. The optical mechanics of road mirages follow predictable patterns that highway engineers could probably calculate if they were so inclined. Light from the bright sky travels downward toward the superheated asphalt. It encounters the extreme density gradient in the thermal boundary layer and gets reflected back upward through total internal reflection. The result is a perfect mirror effect that places blue sky imagery exactly where drivers expect to see dark road surface. Road mirages demonstrate remarkable consistency across different geographic regions and climate conditions. Whether you're driving through Death Valley, crossing Texas highways, or navigating urban parking lots, the same atmospheric physics operates. This happens wherever asphalt reaches sufficient temperatures. The Mirage manufacturing process activates like a natural thermostat. Below certain temperature thresholds, no optical effects occur. Above those thresholds, water illusions appear with mechanical reliability. What makes highway mirages particularly fascinating is their interactive behavior with vehicle motion. As you approach a road mirage at highway speeds, the illusion appears to retreat at exactly the same rate you advance. It maintains constant distance, like an optical carrot dangling just beyond reach. This happens because the mirage image depends on specific viewing angles that change as your position changes. This creates the persistent illusion of water that always remains tantalizingly ahead of your vehicle. Desert sand represents nature's most accomplished solar energy collector. It can absorb and store thermal energy with efficiency that would make any renewable energy engineer envious. Unlike highway asphalt that conducts heat away through underlying concrete and soil, desert sand creates isolated thermal zones. These can concentrate solar energy into temperature extremes approaching those found in commercial ovens. Fine desert sand particles excel at rapid thermal absorption due to their dark colors and massive surface area exposure to direct sunlight. During peak heating conditions, sand surface temperatures can exceed 80 degrees Celsius. That's hot enough to cause immediate blistering of human skin and create thermal conditions more extreme than most industrial heating applications. This concentrated thermal energy gets trapped in the uppermost sand layers. It creates surface temperatures that can differ by 30 degrees or more from air temperatures just 1 meter above. These extreme desert heating conditions generate atmospheric temperature gradients so steep they challenge the fundamental physics of atmospheric stability. The superheated air immediately above scorching sand becomes so much less dense than cooler air above. This creates optical density contrasts that can resemble looking through water into air. These represent perfect conditions for total internal reflection that can make sky imagery appear lying directly on the desert floor. Desert mirages operate on spatial scales that dwarf their highway cousins. While road mirages might extend for hundreds of meters along asphalt surfaces, desert mirages can create optical illusions stretching for kilometers across vast sand expanses. Entire phantom lakes complete with detailed shorelines and convincing water surfaces can appear in the middle of bone-dry desert basins. These create oasis illusions so realistic they've misdirected human travelers throughout recorded history. The persistence of desert mirages also exceeds that of most other atmospheric optical phenomena. Highway mirages fluctuate constantly due to turbulent air currents and passing vehicles that disrupt thermal boundary layers. But desert mirages can remain optically stable for hours at a time when wind conditions remain calm and solar heating continues at maximum intensity. These sustained phantom oases have caused countless navigation errors by travelers who believed they were seeing actual water sources. Archaeological evidence suggests that desert mirages have influenced human migration patterns and settlement decisions for thousands of years. Ancient trade routes occasionally detoured toward locations where persistent mirages created the false impression of water availability. Some desert settlements were established in areas where geographic features created particularly reliable mirage formation. This allowed inhabitants to use these optical phenomena as navigation landmarks for crossing otherwise featureless sand expanses. The most dramatic atmospheric optical effects don't happen high in the sky among clouds and weather systems. They occur in an invisible zone of maximum thermal chaos that extends just 1 or 2 meters above any sufficiently heated surface. This low-altitude refraction layer represents the atmosphere's most concentrated optical workshop. Extreme temperature gradients pack maximum light-bending power into minimum vertical space. Ground-level heating creates what atmospheric physicists call a mixing layer. This represents a thin atmospheric zone where hot air rising from heated surfaces collides with cooler air descending from above. This collision zone becomes a battlefield of competing thermal currents that generate rapid temperature fluctuations across tiny vertical distances. The optical consequences of this thermal warfare include some of Earth's most intense refractive effects. Within this concentrated distortion zone, temperature change by 15 degrees across a vertical distance of just 10 centimeters. That creates refractive index gradients approaching those found in precision optical equipment. This essentially transforms the air immediately above hot surfaces into natural lens systems with focal lengths measured in meters rather than kilometers. The low-altitude concentration of optical effects explains why mirages appear most intense when viewed from ground level rather than from elevated positions. Standing observers experience maximum mirage intensity because their line of sight travels through the entire thickness of the thermal mixing layer. Drivers in tall vehicles or observers on elevated platforms look down through much thinner sections of the refractive zone. This reduces the optical effects significantly. This ground-hugging concentration of atmospheric optical power also explains why mirage photography often proves disappointing compared to direct visual observation. Camera lenses positioned at typical human eye level capture images through the full intensity of the thermal mixing layer. But cameras mounted higher above ground or equipped with telephoto lenses that compress atmospheric perspective often miss the dramatic refractive effects. These create convincing mirage illusions for direct human observation. The narrow vertical extent of maximum mirage intensity creates interesting viewing geometry effects. Observers lying flat on hot ground can experience more dramatic mirage effects than those standing upright. This happens because the prone position maximizes the viewing path through the thermal mixing layer. This geometric relationship explains why some of the most spectacular mirage photographs are captured from very low camera positions. These take full advantage of concentrated ground-level refractive effects. Wind represents the natural enemy of atmospheric optical precision. It can destroy even the most carefully crafted temperature gradients within seconds of its arrival. Like a vandal loose in a delicate optical laboratory, moving air scrambles the layered temperature structures that mirages require. It mixes hot and cool air zones until the precise density arrangements necessary for light bending completely disappear. Calm weather conditions allow heated surfaces to establish and maintain the extreme temperature gradients that sophisticated mirages demand. Without wind to disrupt thermal layering, hot air rising from scorching ground surfaces can arrange itself into stable, stratified zones. These persist for hours at a time. These undisturbed atmospheric conditions create optimal circumstances for total internal reflection and complex light-bending phenomena. The relationship between wind speed and mirage intensity follows predictable patterns that meteorologists can actually forecast. Wind speeds below 8 kilometers per hour allow strong thermal gradients to develop and maintain their optical properties. Moderate winds between 8 and 24 kilometers per hour create turbulent mixing that weakens but doesn't completely destroy mirage effects. Wind speeds exceeding 24 kilometers per hour typically eliminate mirage formation entirely by thorough mixing atmospheric layers. Desert regions excel at providing the windless conditions that premium mirage formation requires. High-pressure weather systems common in desert climates suppress air movement and create the atmospheric stability necessary for maintaining undisturbed temperature layering. These calm conditions can persist for days at a time. This allows complex mirage phenomena to develop fully and create sustained optical illusions. The absence of wind also allows thermal boundary layers to become thinner and more concentrated, intensifying the optical effects that create convincing mirages. When air movement stops, heat rising from ground surfaces forms knife-edge temperature transitions that produce maximum refractive power in minimum vertical space. These compressed thermal gradients can bend light through more extreme angles than the broader, diffused temperature zones that develop under windy conditions. Experienced mirage observers learn to recognize optimal viewing conditions by monitoring atmospheric stability indicators. Smoke rising straight up from distant sources indicates minimal air movement. Distant objects appearing sharp and clearly defined suggest stable atmospheric conditions. The absence of dust or haze movement signals calm conditions that favor mirage development. These natural indicators allow observers to predict when atmospheric conditions will support spectacular optical phenomena. This turns mirage hunting into a scientific pursuit that combines meteorology, atmospheric physics, and optical engineering into a single fascinating outdoor laboratory experience. Oceans function as the planet's most sophisticated climate control systems. They store and release thermal energy with the precision of massive atmospheric engineering installations. Cold seawater possesses an almost magical ability to flip normal temperature relationships completely upside down. This creates atmospheric conditions so unusual they transform marine environments into natural optical laboratories. These laboratories can manufacture impossible visual experiences. The thermal mass of ocean water represents one of nature's most impressive energy storage systems. While land surfaces heat up and cool down rapidly with changing weather conditions, seawater maintains relatively stable temperatures year-round. This happens due to its enormous capacity for absorbing and storing thermal energy. This temperature stability allows oceans to act like planetary thermostats that moderate atmospheric conditions across vast geographic regions. When warm continental air masses flow over cold ocean surfaces, they encounter natural refrigeration. The scale dwarfs any human-engineered cooling system. The frigid seawater rapidly chills the lowest atmospheric layers while leaving warmer air floating above. This creates temperature inversion structures that can extend for hundreds of kilometers across marine environments. These marine temperature inversions establish perfect conditions for superior mirage formation. This represents the optical phenomena that make distant objects appear elevated above their actual positions. Unlike the hot surface inversions that create dancing highway mirages, cold ocean inversions produce stable, long-lasting optical effects. These can maintain their impossible imagery for hours at a time. Arctic and subarctic waters excel at creating the most dramatic marine inversion effects due to their extremely cold surface temperatures. When relatively warm air masses encounter ice-cold polar waters, they create temperature contrasts so extreme they generate atmospheric lenses. These lenses can bend light through angles approaching 30 degrees or more. That's sufficient to make objects beyond the normal horizon appear as clear, detailed images floating in the sky. The stability of marine temperature inversions also allows complex optical phenomena to develop. This would be impossible over land surfaces. Multiple inversion layers can stack on top of each other like optical sandwiches. This creates atmospheric lens systems with several different focal lengths operating simultaneously. This layered architecture enables the extraordinary Fata Morgana displays that occasionally transform ordinary seascapes into impossible floating kingdoms. These come complete with aerial castles and suspended architectural fantasies. Maritime superior mirages represent some of Earth's most spectacular optical performances. They transform ordinary ocean horizons into impossible theaters where ships sail through the sky. Distant islands hover like aerial continents. These appear completely detached from the sea surface. These marine optical illusions operate with such precision and stability they've inspired countless legends throughout history. Legends of ghost ships, floating cities, and magical kingdoms existing just beyond the edge of normal reality. The atmospheric mechanics behind marine superior mirages require temperature inversion conditions. Oceans create these with remarkable consistency during specific weather patterns. Cold seawater chills the lowest atmospheric layers, while warmer air remains floating above. This establishes upside-down temperature gradients that act like enormous horizontal lenses extending across vast marine regions. Light from distant ships sailing beyond the normal horizon gets bent upward by these atmospheric lenses. This creates elevated images that appear to float in the sky above their actual positions. The ships themselves remain hidden below the horizon, but their optical ghosts become visible as detailed aerial phantoms. These can include recognizable features like masts, sails, and hull configurations. Island superior mirages create even more spectacular optical experiences. Distant land masses that should be completely hidden by Earth's curvature can appear as floating aerial territories suspended above the water's surface. These phantom islands often appear inverted. This creates the surreal experience of seeing upside-down mountains and coastlines hanging in the sky. They look like impossible geological formations from alternate dimensions. The clarity and detail of marine superior mirages can be absolutely extraordinary. Unlike the shimmering, unstable images characteristic of hot surface mirages, cold ocean inversions can produce elevated images so sharp and steady they appear indistinguishable from real objects floating in the sky. Ships' crews have reported seeing aerial vessels with such convincing detail. They could identify specific rigging configurations and flag markings on phantom ships sailing through the heavens. Polar exploration history contains numerous accounts of superior mirage phenomena, so complex they completely confuse navigation efforts. Arctic explorers documented entire phantom mountain ranges that appeared and disappeared based on atmospheric conditions. This led to significant errors in mapping polar coastlines. Some reported land masses turned out to be superior mirage images of distant territories. These lay hundreds of kilometers beyond the actual horizon. These created geographical illusions that persisted in exploration records for decades. More accurate surveying methods later revealed the atmospheric nature of these impossible landscapes. Coastal environments occasionally provide free magnification services that would make any telescope manufacturer jealous. They stretch distant objects vertically into impossible proportions. This can make ordinary ships appear as towering maritime skyscrapers. This atmospheric zoom effect operates through precisely calibrated temperature gradients. These function like enormous natural telephoto lenses extending across entire marine regions. Vertical magnification happens when light from distant objects travels through multiple atmospheric layers. These layers have different refractive properties stacked on top of each other. each layer bends light by slightly different amounts. This creates complex optical paths that can stretch images dramatically in specific directions. It leaves them unchanged in others. The result is geometric distortion that makes familiar objects appear transformed into impossible shapes. Ships become particularly susceptible to coastal magnification effects due to their position at the interface between sea and sky. This is where atmospheric optical effects concentrate most intensely. A normal vessel with standard proportions can appear stretched into a vertical tower. It looks more like a floating maritime skyscraper than a conventional ship. The hull might extend upward like an impossible elevator shaft. The superstructure gets compressed into thin horizontal lines floating at various altitudes. Distant coastlines and mountain ranges also fall victim to atmospheric magnification magic. Temperature inversion layers can stretch coastal peaks into needle-like spires. They appear to tower impossibly high above their actual elevations. Entire mountain ranges might appear as vertical walls of rock rising straight up from the ocean surface. This creates geographical illusions that bear no resemblance to the actual topography they represent. The mathematical complexity of predicting vertical magnification effects requires sophisticated atmospheric modeling. This must account for multiple interacting temperature gradients operating simultaneously. Unlike simple superior mirages that follow relatively straightforward optical rules, vertical magnification involves complex interactions. These occur between several different refractive layers. These can produce almost unlimited varieties of impossible geometric distortions. Antarctic research stations have documented some of Earth's most extreme coastal magnification phenomena. Research vessels approaching these facilities occasionally appear as impossibly tall vertical structures. They stretch from the ocean surface up to the clouds like maritime space elevators. Distant icebergs transform into towering ice cathedrals. They bear no resemblance to their actual low-profile configurations. This creates optical experiences so bizarre they challenge observers' fundamental understanding of how familiar objects should appear in normal visual reality. Ocean environments refuse to remain optically static. Instead, they operate like enormous natural film editing systems that continuously modify atmospheric optical effects in real time. Tidal cycles, ocean currents, and changing water temperatures create dynamic marine conditions. These can make superior mirages appear, disappear, transform, and morph. These unfold like atmospheric movies spanning several hours. Tidal movements create constantly shifting temperature boundaries as different water masses move across marine regions. Incoming tides can bring cooler or warmer water that establishes new temperature inversion patterns. Outgoing tides expose different thermal zones that modify atmospheric optical conditions. These tidal temperature changes can make superior mirages strengthen, weaken, or completely disappear. This can happen within time frames measured in minutes rather than hours. Ocean currents function like massive underwater conveyor belts that transport water masses with different temperatures across vast distances. When warm currents encounter cold regional waters, or when cold currents flow into warmer marine zones, they create temperature boundary effects. These can establish or destroy the precise atmospheric conditions necessary for complex mirage formation. The Gulf Stream represents one of Earth's most powerful mirage-affecting ocean currents. It transports warm tropical water northward along the eastern coast of North America. Where this warm current encounters colder northern waters, it creates marine temperature contrasts. These can generate spectacular superior mirage displays. Ships sailing through these Gulf Stream boundary zones occasionally experience rapid sequences of optical effects. This happens as they cross from one temperature regime to another. Seasonal ocean temperature cycles also influence the types and intensity of marine mirages that different coastal regions experience throughout the year. Arctic waters produce maximum superior mirage activity during summer months when relatively warm air masses flow over ice-cold polar seas. Tropical regions might experience peak marine optical effects during winter months when cooler air encounters warm ocean surfaces. Weather fronts moving across ocean surfaces can create particularly dramatic real-time changes in atmospheric optical conditions. The passage of a cold front can rapidly establish strong temperature inversions. These generate superior mirages within hours of the weather system's arrival. Conversely, warm fronts can destroy existing inversion layers and eliminate mirage effects. This can happen just as quickly as they establish them. This creates dynamic optical experiences that change faster than observers can document them photographically. Modern cities have accidentally evolved into some of Earth's most efficient atmospheric optical laboratories. Millions of tons of concrete, asphalt, and steel collaborate to create urban heat islands that can manufacture mirages with industrial-scale consistency. These metropolitan environments don't just modify local weather patterns. They transform entire urban regions into massive mirage production facilities that operate 24 hours a day during appropriate seasonal conditions. Urban heat islands develop through the impressive thermal absorption capabilities of artificial building materials. Concrete absorbs and stores solar energy like a geological battery system. Asphalt surfaces can reach temperatures exceeding those found in natural desert environments. Steel and glass buildings add their own thermal contributions by concentrating and reflecting solar radiation into focused heat zones. These can create localized temperature extremes approaching those found in commercial ovens. The cumulative effect of these urban heating elements creates atmospheric temperature gradients that can exceed those found in most natural environments. Downtown business districts surrounded by acres of heat-absorbing pavement and radiation-reflecting buildings establish thermal conditions capable of generating superior mirages. These make distant skyscrapers appear to float above the urban landscape like impossible aerial architecture. City planners and architects have unknowingly designed optimal mirage formation environments through their material choices and urban layout decisions. Wide boulevards lined with heat-reflecting glass towers create thermal corridors where extreme temperature gradients can develop and persist throughout daylight hours. Parking structures and rooftop installations add elevated heat sources that contribute additional thermal complexity to urban atmospheric conditions. Metropolitan mirage phenomena follow predictable patterns based on urban geography and architectural density. Downtown cores generate the most intense effects due to concentrated building masses and minimal vegetation. Suburban areas with more scattered development produce weaker, but still observable optical effects. Industrial zones with extensive concrete and metal surfaces can create mirage conditions rivaling those found in natural desert environments. Traffic patterns also influence urban mirage formation through the additional heat generated by millions of internal combustion engines operating simultaneously. Rush hour periods can intensify urban heat island effects significantly, creating peak mirage formation conditions that coincide with maximum human observation opportunities. The combination of concentrated vehicle exhaust heat and extensive artificial surface heating creates urban atmospheric conditions. These can support spectacular optical phenomena throughout the warmest months of the year. Urban environments have inadvertently created the world's largest unplanned optical engineering projects. Thousands of reflective building surfaces collaborate with atmospheric refraction to produce compound mirage effects that multiply and amplify natural optical phenomena. These artificial reflection systems don't just create simple mirror images. They generate complex optical interactions that can produce layered visual illusions more sophisticated than anything found in natural environments. Glass-walled skyscrapers function like enormous vertical mirrors that can redirect and concentrate solar radiation into focused heat zones stretching for city blocks. When these concentrated thermal zones interact with atmospheric temperature gradients, they create localized mirage formation areas that wouldn't exist without human architectural intervention. The combination of artificial heating and natural atmospheric physics produces hybrid optical phenomena. These represent entirely new categories of mirage formation. Modern building materials excel at creating the precise thermal conditions that sophisticated mirage formation requires. Polished steel surfaces can reach temperatures approaching 80 degrees Celsius during peak solar heating. Adjacent glass panels create complex patterns of reflected and concentrated solar radiation. These architectural heat sources establish multiple overlapping temperature gradients that can generate superior mirages with several different focal points operating simultaneously. The geometric arrangement of urban reflective surfaces creates optical multiplication effects where single objects can appear as multiple images. This happens through different atmospheric and artificial reflection paths. Distant buildings might appear simultaneously as elevated superior mirage images and as traditional mirror reflections from nearby glass surfaces. This creates composite visual experiences that combine natural atmospheric optics with human-engineered reflection geometry. Office building clusters create particularly complex compound optical environments where dozens of reflective surfaces interact with atmospheric temperature gradients. These produce optical effects that can change dramatically throughout the day as solar angles shift. Morning sun angles might establish one set of reflection and refraction patterns. Afternoon solar positions create entirely different optical configurations that transform the same urban landscape into different varieties of impossible visual experiences. Urban planners working in cities known for spectacular mirage phenomena have begun considering atmospheric optical effects in their design processes. Some architectural projects now deliberately incorporate reflective surface positioning that can enhance natural mirage formation. This creates urban environments designed to optimize rather than accidentally produce spectacular atmospheric optical displays. These intentionally optical cities represent the first examples of human settlements designed specifically to collaborate with natural atmospheric physics in creating enhanced visual experiences. Cities have unknowingly constructed vast networks of artificial desert surfaces. These can generate thermal conditions more extreme than those found in most natural arid environments. Parking lots, sports complexes, airport runways, and interconnected street systems create distributed heat generation networks. These cover hundreds of square kilometers with materials specifically optimized for solar energy absorption and thermal storage. Shopping mall parking lots represent some of urban civilization's most impressive mirage generation facilities. These vast asphalt expanses can reach surface temperatures exceeding 75 degrees Celsius during peak summer conditions. This creates thermal energy storage systems that continue radiating heat long after sunset. The combination of massive thermal mass and minimal vegetation allows these artificial dead zones to maintain extreme temperature gradients. These support consistent mirage formation throughout extended periods. Sports stadiums and recreational facilities contribute additional artificial heating elements through their extensive use of synthetic playing surfaces and surrounding asphalt infrastructure. Football fields with artificial turf can reach surface temperatures approaching 90 degrees Celsius. Surrounding parking areas add thousands of additional square meters of heat-absorbing surfaces. These recreational complexes essentially function as concentrated thermal energy production facilities during sporting events and other large gatherings. Airport environments create some of the most extreme urban thermal conditions. They combine vast asphalt runway systems with concentrated jet exhaust heating. Commercial aircraft engines produce localized temperature spikes that can exceed 200 degrees Celsius. Runway surfaces covering thousands of hectares provide massive thermal storage capacity. These aviation facilities can generate atmospheric conditions capable of supporting spectacular mirage phenomena that occasionally interfere with pilot visibility during critical flight operations. The interconnected nature of urban asphalt networks creates thermal multiplication effects. Heat generated in one area gets conducted and radiated across vast urban regions. But street systems function like thermal distribution networks that can transport and spread concentrated heat throughout metropolitan areas. During peak summer conditions, these asphalt networks can create city-wide temperature elevation effects. These establish optimal mirage formation conditions across entire urban regions simultaneously. Urban heat management research has revealed that strategic modification of asphalt surface properties can significantly influence local mirage formation patterns. Light-colored pavement materials and specialized cooling additives can reduce thermal absorption and minimize optical effects. Traditional dark asphalt surfaces continue generating the extreme heating conditions that support dramatic atmospheric optical phenomena. Some cities have begun using asphalt thermal management as a deliberate tool for controlling local atmospheric optical conditions. Modern cities contain millions of hidden thermal warriors working around the clock to create localized temperature chaos. This adds layers of optical complexity to urban atmospheric conditions. Air conditioning systems, industrial exhaust vents, vehicle cooling systems, and mechanical equipment installations pump concentrated heat into urban environments at thousands of discrete locations. This creates a distributed network of artificial thermal pollution that can significantly amplify natural mirage formation processes. Commercial air conditioning systems represent some of the most powerful artificial heat sources operating in urban environments. Large office buildings and shopping complexes can exhaust thermal energy equivalent to several hundred residential heating systems operating simultaneously. This concentrated waste heat gets discharged directly into the urban atmosphere through rooftop installations and street-level venting systems. It creates localized hot spots that can establish extreme temperature gradients within meters of their discharge points. Vehicle exhaust systems add mobile thermal contributions that create constantly shifting patterns of localized heating throughout urban transportation networks. During peak traffic periods, Concentrated vehicle exhaust can raise local air temperatures by 10 degrees or more above ambient conditions. These mobile heat sources create dynamic thermal patterns that can establish temporary mirage formation zones. These appear and disappear based on traffic density and movement patterns. Industrial facilities and power generation systems contribute additional concentrated thermal sources through their cooling tower operations, exhaust stacks, and waste heat recovery systems. These industrial heat sources can operate continuously throughout day and night cycles. They maintain localized temperature elevation effects that persist long after natural solar heating diminishes. The combination of industrial waste heat and urban thermal storage creates hybrid heating conditions. These can support mirage formation during extended periods when natural heating alone would be insufficient. The cumulative effect of multiple artificial heat sources operating simultaneously throughout urban environments creates thermal complexity. It far exceeds what natural heating processes alone could generate. Dozens of air conditioning units operating on a single city block can establish overlapping temperature gradient patterns. These create multiple mirage formation zones within areas smaller than a single urban intersection. Urban atmospheric monitoring systems have revealed that artificial heat sources can account for temperature elevation effects. These approach those created by natural solar heating during peak summer conditions. Cities essentially operate as massive distributed heating systems that can maintain elevated atmospheric temperatures throughout extended periods. This creates optimal mirage formation conditions that persist longer and with greater intensity than comparable natural heating environments. This artificial thermal amplification allows urban environments to produce spectacular optical phenomena. These rival or exceed those found in traditional desert mirage formation regions. Hot air refuses to remain invisibly well-behaved when temperatures climb high enough. Instead, it begins performing a constant atmospheric dance that makes the entire world appear to shimmer and vibrate. Reality itself seems to develop a case of optical hiccups. This heat shimmer phenomenon represents one of the most common yet least understood atmospheric optical effects. It turns every sun-baked surface into a natural demonstration of air density chaos that our eyes can actually see. Heat shimmer operates through the same density fluctuations that create mirages, but instead of producing stable optical illusions, it generates constantly changing refractive effects. These make distant objects appear to wiggle, dance, and vibrate. The superheated air immediately above hot surfaces becomes so thermally unstable that it creates rapidly fluctuating density patterns. These patterns bend light through constantly changing angles. Unlike the steady temperature gradients that produce consistent mirage effects, heat shimmer results from turbulent mixing. Hot air rising from heated surfaces collides chaotically with cooler air above. This thermal collision zone becomes a battlefield of competing air currents that generate rapid density fluctuations. These occur across time scales measured in fractions of seconds rather than minutes or hours. The visual effects of heat shimmer become most apparent when observing distant objects through these zones of atmospheric turbulence. Buildings, trees, vehicles, and people appear to dance and undulate. Light from these objects gets bent through continuously changing angles during its journey through the unstable air. The objects themselves remain perfectly stationary, but their images arrive at your eyes via constantly shifting optical paths. This makes them appear to move. Astronomical observations suffer significantly from heat shimmer effects which astronomers call seeing conditions. Ground-based telescopes must contend with atmospheric turbulence. It makes stars appear to twinkle and causes detailed planetary observations to become blurry and unstable. The same thermal instability that creates entertaining visual effects on hot summer days represents a serious obstacle for precision optical observations of celestial objects. Professional photographers and videographers learn to recognize and work around heat shimmer effects when shooting in hot environments. Camera operators understand that telephoto lenses amplify heat shimmer effects by compressing the optical path through turbulent air zones. Wide-angle lenses minimize these distortions by reducing the relative impact of atmospheric instability. Understanding heat shimmer behavior allows visual artists to avoid these effects when unwanted. They can also deliberately incorporate them for specific atmospheric mood creation in their imagery. The atmosphere occasionally abandons its single-effect approach to optical illusions. Instead, it stages elaborate multimedia presentations where rainbows, sundogs, halos, and mirages all perform simultaneously in coordinated displays. These transform ordinary skies into impossible art galleries. These complex atmospheric optical combinations represent some of nature's most spectacular visual productions. Multiple physical phenomena collaborate to create experiences that challenge observers' understanding of what reality should look like. Rainbow formation requires completely different atmospheric conditions than typical mirage formation. Rainbows need water droplets suspended in air, while mirages need temperature gradients and density variations. But when specific weather patterns align properly, both phenomena can occur simultaneously. This creates the extraordinary experience of seeing rainbow arcs floating above phantom landscapes or colored light spectra reflected in mirage water illusions. Sundogs and atmospheric halos add additional complexity to these optical performances through their interaction with ice crystals suspended in high-altitude cirrus clouds. These ice crystal phenomena can create multiple false suns, circular light rings around the actual sun, and colored arcs displays. These appear to intersect with superior mirage images floating above the horizon. The result is layered optical experiences where reality becomes completely scrambled among multiple competing visual effects. Lunar optical phenomena can combine with nighttime mirage effects during specific atmospheric conditions. They can create some of the most bizarre natural light shows on Earth. Moon dogs, lunar halos, and moonbow displays occurring simultaneously with nocturnal temperature and mirages produce ethereal optical experiences. These seem more appropriate to science fiction than natural atmospheric physics. The photography of combined atmospheric optical phenomena presents unique technical challenges because different effects often require conflicting exposure and focus settings. Capturing sharp mirage details while simultaneously recording faint rainbow or halo effects demands sophisticated camera techniques. This often requires multiple exposure combination methods. Some of the most spectacular atmospheric optical photographs result from patient photographers who position themselves strategically during rare weather conditions. Arctic and polar regions experience the most dramatic combinations of atmospheric optical effects due to their unique meteorological conditions. These can support ice crystal phenomena, temperature inversion mirages, and unusual solar angle effects simultaneously. Polar explorers and researchers regularly document extraordinary optical displays that include multiple types of mirages, various halo phenomena, and unusual light refraction effects. All of these operate together in single coordinated atmospheric performances that can persist for hours at a time. The atmosphere's optical performance depends critically on what's floating around between you and the phenomena you're trying to observe. Even invisible particles too small for human eyes to detect individually can dramatically influence mirage formation, clarity, and stability. Clean air acts like premium optical glass that allows sophisticated atmospheric illusions to develop with maximum clarity. Particle-laden air functions like frosted glass that can blur, weaken, or completely destroy even the most dramatic temperature gradient effects. Dust particles represent the most common atmospheric optical saboteurs in terrestrial environments. Desert regions that excel at creating extreme temperature gradients for mirage formation often simultaneously generate airborne dust that can severely compromise optical transparency. The irony is that the same wind-free conditions allow optimal mirage development. They also permit dust particles to remain suspended in the atmosphere longer. This creates a fundamental conflict between optimal thermal conditions and optimal optical clarity. Water vapor operates as a more subtle but equally important factor in atmospheric optical quality. Humid air contains millions of microscopic water droplets that scatter light through Rayleigh scattering processes. This reduces contrast and blurs fine details in atmospheric optical phenomena. Desert environments provide optimal mirage conditions partly because their extremely low humidity maintains maximum atmospheric transparency. This is necessary for observing temperature gradient optical effects. Industrial pollution and urban air quality significantly impact mirage observation possibilities in metropolitan environments. Particulate emissions from vehicles, manufacturing facilities, and power generation systems can create persistent atmospheric haze. This eliminates the optical clarity necessary for observing sophisticated urban heat island mirages. Ironically, cities that generate ideal thermal conditions for mirage formation often produce air quality conditions that prevent clear observation. These conditions hide the optical phenomena they create. Volcanic eruptions and major dust storms can eliminate atmospheric optical phenomena across vast geographic regions. They inject massive quantities of light-scattering particles into the atmosphere. These events can suppress mirage formation and visibility across areas covering thousands of square kilometers. This demonstrates how atmospheric particle content controls optical phenomena more powerfully than temperature gradients alone. Professional atmospheric optics researchers monitor air quality conditions as carefully as they monitor temperature and pressure patterns when planning observation expeditions. Particle counters, visibility measurements, and atmospheric transparency monitoring equipment allow scientists to predict optimal viewing conditions for sophisticated mirage phenomena. The clearest atmospheric conditions often occur immediately after weather fronts pass through regions. They clear airborne particles and establish maximum optical transparency for observing temperature gradient effects. The sun's position in the sky acts like a cosmic spotlight director. It determines when and how dramatically atmospheric optical phenomena will perform for human audiences. Solar angle relationships control not just the intensity of surface heating that creates temperature gradients. They also control the viewing geometry that determines whether observers can actually see the optical effects that atmospheric conditions generate. Low solar angles during sunrise and sunset periods create optimal conditions for observing superior mirages and other elevation-dependent optical phenomena. When the sun hangs near the horizon, It illuminates objects through maximum atmospheric path lengths. It also creates the shallow viewing angles necessary for observing atmospheric lenses. These lenses operate most effectively when viewed nearly horizontally across their refractive surfaces. Morning atmospheric conditions often provide ideal mirage observation opportunities due to the combination of overnight radiative cooling effects and increasing solar heating. The temperature inversion layers established through nighttime cooling can persist into early morning hours. Sunrise illumination then begins creating the thermal gradients necessary for optical phenomena. This transition period creates layered atmospheric conditions that can support complex mirage effects unavailable during other times of day. Midday solar positions create maximum surface heating, but often establish viewing geometries that make atmospheric optical effects difficult to observe clearly. High solar angles produce steep viewing angles down through thermal boundary layers, rather than the shallow horizontal viewing paths that maximize optical effects. The paradox is that peak thermal conditions for mirage formation often coincide with poor viewing geometry for observing the phenomena those thermal conditions create. Seasonal variations in solar angle patterns influence the types and timing of atmospheric optical phenomena that different geographic regions experience throughout the year. Arctic regions experience extended periods of low solar angles that can create optimal superior mirage viewing conditions for months at a time. Tropical regions experience more consistent solar angle patterns that favor different types of optical phenomena depending on seasonal weather pattern changes. These depend on seasonal weather pattern changes rather than solar geometry variations. Professional mirage photographers and atmospheric optics enthusiasts time their observation efforts based on solar angle calculations. They also use seasonal patterns specific to their geographic locations. Optimal viewing conditions for specific types of atmospheric optical phenomena can be predicted with astronomical precision. This combines solar position calculations with local topography and typical weather pattern information. This scientific approach to atmospheric optics observation transforms mirage hunting from random chance encounters into predictable natural phenomenon observation expeditions. The atmosphere follows an annual rhythm as predictable as any natural migration pattern. Different seasons create optimal conditions for specific types of mirage formation based on changing weather patterns, solar heating angles, and atmospheric stability characteristics. Understanding these seasonal optical cycles allows observers to predict when and where different atmospheric phenomena will reach peak performance levels throughout the year. Spring atmospheric conditions create transitional optical environments where winter temperature inversion patterns begin breaking down while summer heating effects gradually establish themselves. This transitional period can produce complex, layered atmospheric structures that support exotic mirage phenomena unavailable during more stable seasonal periods. The competition between cooling and heating effects creates atmospheric instability that can generate rapidly changing optical displays. Summer represents peak season for inferior mirage formation due to maximum solar heating and optimal high-pressure weather patterns that suppress atmospheric turbulence. Desert regions, urban heat islands, and highway environments reach optimal thermal conditions during summer months. These conditions create extreme temperature gradients that support spectacular inferior mirage displays. The combination of maximum heating and stable atmospheric conditions creates ideal circumstances for sustained mirage observation. Autumn atmospheric conditions often provide optimal opportunities for superior mirage observation due to the increasing frequency of temperature inversion situations. These are created by radiative cooling effects and changing weather pattern stability. The transition from summer heating dominance to winter cooling dominance creates atmospheric conditions that can support complex, elevated mirage phenomena. This is particularly true in coastal and marine environments. Winter mirage activity depends heavily on geographic location and local climate characteristics. Arctic and subarctic regions can experience peak superior mirage activity during winter months. Extreme temperature contrasts between cold surfaces and relatively warm air masses create optimal inversion conditions. Temperate regions might experience minimal mirage activity during winter due to reduced solar heating and increased atmospheric turbulence from winter storm patterns. Meteorological research has revealed that long-term climate patterns and seasonal weather variations create predictable annual cycles in atmospheric optical phenomena. These can be mapped and forecasted like traditional weather patterns. Some regions experience reliable mirage seasons when atmospheric conditions consistently support optimal optical phenomena formation. Other areas show more random seasonal patterns dependent on specific weather system movements and atmospheric stability characteristics. These vary significantly from year to year based on larger climate oscillation patterns. What began as curiosity about impossible optical illusions has evolved into a sophisticated scientific discipline. It provides valuable insights into atmospheric structure, temperature distribution patterns, and weather system behavior. These would be difficult or impossible to obtain through traditional meteorological instruments alone. Modern atmospheric scientists use mirage observation and analysis as natural atmospheric probes. These reveal invisible air characteristics with precision that complements conventional weather monitoring technology. True. Temperature gradient measurement represents one of the most valuable scientific applications of mirage research. By analyzing the optical characteristics of atmospheric mirages, their intensity, stability, and geometric properties, scientists can calculate precise temperature profiles. These extend throughout the atmospheric boundary layer. This accuracy approaches that of balloon-borne temperature sensors. This optical thermometry technique provides continuous real-time atmospheric temperature monitoring without requiring physical instrument deployment. Atmospheric turbulence analysis benefits significantly from heat shimmer and mirage instability studies that reveal air movement patterns invisible to conventional wind measurement instruments. The dancing and fluctuation characteristics of atmospheric optical phenomena provide detailed information about small-scale atmospheric mixing processes. These influence weather development, air quality dispersion, and aviation safety conditions. Weather prediction modeling incorporates atmospheric optical phenomenon data as validation tools for computational atmospheric simulation accuracy. When weather models successfully predict optimal mirage formation conditions that match actual observed atmospheric optical phenomena, this confirms their accuracy. It shows the models correctly represent atmospheric temperature and stability structure. Discrepancies between predicted and observed optical conditions reveal model inaccuracies that can lead to improved weather forecasting algorithms. Climate research uses long-term atmospheric optical phenomenon records as proxy indicators for historical temperature and atmospheric stability patterns. This matters most in regions where conventional meteorological records don't exist. Historical accounts of mirage observations, particularly from maritime exploration records and desert travel narratives, provide valuable data about past atmospheric conditions. These complement traditional paleoclimate reconstruction methods. Aviation safety research relies heavily on atmospheric optical phenomenon studies to understand and predict visibility conditions that can affect flight operations. Clear air turbulence, wind shear detection, and thermal soaring condition prediction all benefit from this research. It focuses on the atmospheric conditions that create various types of optical phenomena. Understanding the relationship between atmospheric optics and air movement patterns helps improve aviation weather services. It also improves flight safety protocols that protect aircraft operations in challenging atmospheric environments.